So I'm sharing my entire screen here. We'll use that. So to begin with, I'll okay. So these are the things we have discussed in the last class. We talked about the idea of stress tensor. Stress tensor. For that, what did we do? We chose an object, a body, and we wanted to define stress at point Q. So to do that, we have split the body into 8 parts. Well, our objective is not to divide the body into 8 parts. We used 3 mutually perpendicular planes to cut the body at Q. And we have defined force per unit area, or what we usually call stress, in each of the plane in all 3 directions. So 3 directions in the plane perpendicular to x-axis, 3 direction in the plane perpendicular to y-axis, 3 direction in the plane perpendicular to z-axis. So a total of 3 components. We figured out that so there are a total of 3 components each on 3 components on each plane, and total of 9 components. And we called it a tensor, stress tensor. And after that, these were plotted on a general volume element, a very infinitesimally small element. We have drawn all those stress components. I told you that tau xx, which is normal stress on each plane, can also be called sigma x. So these are the three mutually perpendicular planes we drew here. Those are those 3 here. 1, 2, 3. 1, 2, 3. And you also have 3 planes on the other side of the element here. For them also, the same value of stress can be given just like the opposite side. If this is sigma x, this is again sigma x in the opposite direction. If tau xy is upward here, tau xy is downwards there. That's the way it works. And finally we figured out that there is these many of the components in the stress tensor are equal. Means the stress tensor matrix is symmetric. Tau xy is equal to tau yx, tau xz is equal to tau zx, and tau yz is equal to tau zy. And for a 2D case, we can remove third row and third column, and the tensor becomes sigma x, tau xy, tau yx, sigma y. Again, tau xy and tau yx are same, and you can use it interchangeably. Or you can simply write tau. There is no need of xy. In the 2D case, because both are same, you can simply write tau. So this figure, the element, this here is a 3D element. You can also plot a 2D element just the way we have done here, and this is how it looks like: sigma x, sigma y, and tau xy, tau yx, which are the shear stresses. Now I hope you've understood what we have discussed so far. If you haven't, you need to ask questions. Now let's go ahead and continue with the I'll just open our textbook here. Okay, so in case if we need some figures, we can take it from here. It's very difficult to draw figures in computer. I mean manually by freehand writing it's difficult, so I'll take some images from here. I'll note down okay. I think I shared you this PDF, right? PDF of this textbook. Have I? Oh, it's not given here. Okay, I'll share you the PDF. No issue. I think I talked about this. This is an excellent textbook. All right. Now what we are going to do is that as a continuation from the previous class, in the previous class we had taken an arbitrary object, arbitrary body to define stress on it, and it was a three-dimensional object, and hence we got a very general definition. Now in this class we will choose a special case, a real world problem, but a 2D case, and we'll try to find out the stress tensor for that body at a point. That's our objective here. So the trying to join. Okay. What should be the thickness of this pen? If you have any suggestions, you can tell me. I think this is okay, right? Yeah. So what we have is a bar, axial bar, which is being pulled in either direction with a force P. And what is the cross sectional area here? A is the cross sectional area of the bar. Now we want to define stress at a point inside the bar, and we want to see how it looks like. And this is a 2D case. We are avoiding the the dimension out of the plane is being avoided. So we will not have three mutually perpendicular planes here. Instead, we will have two mutually perpendicular lines. Okay, so let's make the cut here. We have cut the bar here, and let's see what is the value of stress on this plane. Using which we have cut the bar. And what is the angle at which we have cut? This angle here is theta. So if we make the cut this way, we can draw the free body diagram. Of the cut section of the bar on the left side. Now question here is, what are the, on the left side you have force, external force P. On the right side, since we have cut the object, there are going to be internal stresses. So we need to find out what are those internal stresses. And if A is the cross sectional area of the bar, what will be the area of this cut section? This angle is theta. If this area is A, area of the cut section will be A divided by cos theta, right? Because the inclined area cos theta will be the value of cross sectional area, hence A by cos theta will be the area of the inclined surface here. Now we would like to get the value of normal stress on this plane and also shear stress on this plane. And what will be this angle here? And that is going to be theta. Since this must follow, this part is in equilibrium, hence net force in each direction should be 0. So if this is P here, the resultant of these two must be P here, which means this should be P cos theta. This means the force, okay, and this value should be P sin theta. Now the question here is, what are the corresponding stress values? We have obtained the force value here, but what we actually need is stress. What we need is sigma theta and tau theta. So if we have a force, how will we find out stress? That will be force divided by area. Hence, sigma theta will be equal to P cos theta divided by area. Area is nothing but A divided by cos theta. And that will be equal to P by A cos square theta. And tau theta is equal to P sin theta divided by A divided by cos theta, and that is P by A sin theta cos theta. So we have obtained the stress values on either sides. I mean stress values on the plane using which we have cut the object, the normal stress on that plane, and also the shear stress on that plane. Now have we done everything required to get stress values on the plane? In 2D we need sigma x, sigma y and tau, right? Tau xy is equal to tau yx. So there is only one tau value actually, which is what we have obtained here. But for sigma we are going to have one more value, which we will call sigma theta minus 90. What is sigma theta minus 90? To get sigma theta minus 90, you need to cut the bar using a plane perpendicular to the plane we have just used, and on that surface you will have sigma theta minus 90. Okay, so it's like sigma x and sigma y. So this is the plane, and on that plane you have sigma theta, and this is a plane perpendicular to the first plane, hence sigma theta minus 90. And what will be that value? And you will see that if this is P cos theta, this is going to be P sin theta, and the cross section area is going to be A by sin theta, equal to P sin theta divided by A by sin theta, and finally P by A sin square theta. Now we have obtained all values, stress values. Now let's plot the element. What is the orientation of the element here? let's say this is a very small element within the bar at this point, and we have seen that for a plane perpendicular to this plane or this plane here, we have obtained stress value as P by A cos square theta, P by A cos square theta, and for this component we have P by A sin square theta. So this surface, and for shear stresses we have P by A sin theta cos theta. So this is how it works. Now since we have used the angle theta, which is a variable, you can change the value of theta and get the matrix. What will be the tensor now? The tensor is nothing but sigma theta tau theta sigma theta minus 90. So this is our stress tensor, and since the theta is a variable here, let's say for the simplest case, let's say theta is 0. If theta is 0, what are the corresponding values of stresses here? If theta is 0, theta is equal to 0. If theta is equal to 0, P by A cos square theta will be 1, cos theta will be 1, cos square theta will be 1, and hence this stress value will be P by A, and sin 0 is 0, therefore in vertical direction stress is 0. Sin theta cos theta, what will be sin theta cos theta? Sin 0 cos 0 is 1, sin 0 is 0, and hence that is also 0. All these shear stress values will also be 0. Now a question we would like to address is, what will be the maximum value of sigma here? If theta is varying, you can simply find the derivative of sigma x here, and you will see what is the maximum value of sigma x. That is nothing but P by A. Cos theta has a maximum value of 1, therefore the maximum value of P by A cos square theta is going to be P by A. So sigma max will be P by A. And what will be tau max? What will be the maximum value of shear stress? P P by A sin theta cos theta, right? P by A, what we need to find out what is the maximum value of P by A sin theta cos theta. So you can differentiate d theta divided by P by A sin theta cos theta. Let that be equal to 0. And you can use the product rule, derivative of sin theta. I think you will get like this. There will be two terms. No, sorry. You don't need to find the derivative on both sides. Product rule means first derivative of sin theta multiplied by cos theta plus sin theta multiplied by derivative of cos theta equal to 0. That's very straightforward. Then you'll see that you'll get tan theta equal to plus or minus 1, and the theta is obviously plus or minus 45 degree. So this is the angle at which you will get the maximum value of shear stress. And which is that location? If theta is equal to 45, we'll plot that. If theta is equal to 45, here at the maximum value of normal stress, the value is P by A, but normal stress on the plane perpendicular to that was 0, and shear stress was also 0. Here for the maximum value of shear stress is happening at theta is equal to 45 plus or minus 45, and if you put 45 back in here, you will get tau max as sin 45 cos 45 1 by root 2. Both are 1 by root 2. 1 by root 2 multiplied by 1 by root 2 will be 1 by 2. So the maximum value of tau will be P by 2A. Hence this value will be P by 2A. And what is the value of normal stress when theta is equal to 45? Normal stress values are P by A, sin square theta and cos square theta. So both sin theta and cos theta are 1 by root 2. Therefore, normal stress values are also going to be P by 2A. P by A into sin square theta, correct? Is that right? Theta is equal to 45. Theta, that should be right. So the maximum value of shear stress is has the half the magnitude of maximum value of normal stress, and that is happening at a angle which is non-zero. Some to be precise, that happens at theta is equal to 45. So just to write the stress tensor here, P by A 0 0 0. So here sigma theta is P by A, sigma theta minus 90 is 0, tau values are 0. And here in the second case, when theta is equal to 45, P by A sin square theta. So here sigma theta is P by 2A, tau which is also tau max, that is P by 2A, tau xy is equal to tau yx, therefore P by 2A, sigma theta minus 90, that is also P by 2A. So all components are P by 2A here. So this is very interesting. So we wanted to define stress at a point for a special case, for a specific problem like this, where a bar is being pulled by some force on either sides which is equal to P, and we figured out that depending on theta, our stress tensor changes. If theta is equal to 0, this is our stress tensor. If theta is equal to 45, this is our stress tensor. And if theta is some other value, our stress tensor also will be different. Then that's a problem, right? So we would like to see what is the value of stress at a point, and we get a matrix for it, and that matrix changes depending on the direction of the cut plane, direction of the plane using which we are cutting the object. And this is something we would like to resolve. So what do we do here? So there is no solution here as such. The stress will be different, the stress tensor will be different depending on the coordinate which we choose to define stress. In the first case, when theta is equal to 0, this was our coordinate, and when theta is equal to 45, this is our coordinate. And when the coordinate rotates, the value of stress tensor changes. Now we can do a problem, or Any questions here? So to get a better understanding of this idea, better understanding of what? When we change the coordinate, the stress tensor changes. To resolve this problem, to get a better idea of why this is happening and how to define stress, we will introduce an idea called the Mohr circle. That's what we are going to do next. So it will take some time for the derivation. Okay, I think today we'll stop. Okay, derivation for Mohr circle is a little lengthy. If I start now, I'll take some time to finish it. So it's better to start in the next class. Yeah, any questions?